In every time and in every circumstance, human beings create their heroes, legends, and myths. Sometimes these arise from the exploits on the field of battle, sometimes in the halls of power. A rich source of such tales is the stories about travel and exploration. Indeed, our own title arises from just such a story. More rarely, though, legends and myths arise from the realm of intellectual pursuit. There is the story of the Jewish scholar who burned many lamps of oil to reconcile one of the books of the Old Testament with the broader biblical canon of his time. And of course, there is the oft-repeated tale of the 70 Jewish rabbis who, as descendants of those who fled the Babylonian sack of Jerusalem to take up residence in exile in Alexandria, each independently translated what is now known as the Old Testament from Hebrew to Koine Greek. In a mere 70 days, each emerging with an identical copy as directed, it was said, by the Spirit of God. This Septuagint, as it was known, became the basis for the Greek Two Testament Bibles of the early Christian Church. It was this church, of course, also, that promulgated the legend, one usually contradicted by the Jewish community, who asserts the translation effort was the result of the scholarly community, something much less divinely inspired and more likely to be the truth. This is often the case with myths and legends. Already noteworthy deeds and accomplishments are exaggerated and puffed up to superhuman efforts. Hercules is no longer just a great warrior. He is the son of God who can divert rivers and ascend to Olympus. Romulus isn't just a tribal leader who organizes a crossroads settlement, but the son of Mars who founds the greatest city in all of the world. Jewish scholars aren't just translating one of the most intricate and difficult pieces of literature and theological work created, but they have to do it all by themselves, each in their own cell, to come out with the same copy. In each case, there is likely some nugget or kernel of truth, a real figure or figures who did real things, but so much has been added that the recovery of that historical person is next to impossible. So too the case in the area of intellectual pursuits. In spite of ancient sources that claim amazing feats of intellectual agility and engineering brilliance, modern investigators have been unable to reproduce the mirrors, catapults, and pulleys Archimedes is said to have used to protect the city of Syracuse in the Second Punic War from Roman invasion. The same can be said for the kite-flying electrical investigations of Dr. Benjamin Franklin. As we have mentioned in a previous episode, there is an enduring scholarly debate regarding whether Galileo actually climbed the stairs of the famous Basilica Tower in Pisa to drop objects of differing mass or density, an experiment we know Riccioli did in the spirit, if not in the actuality, of dropping objects from that same tower. Riccioli's experiment, of course, was from a different tower, but with much greater precision of measurement. In science, the greatest of these legends takes place in an apple orchard in the English province of Lincolnshire, and, as was the case with Galileo, it was first told by a student. In this story, it is the seemingly unremarkable man, someone studying for the Bachelor of Arts at Cambridge University, staying at home, who is sitting in the orchard one evening near sunset. Over the western horizon hung a crescent moon, and in the crisp autumn air the stem of an apple broke. As the apple fell from the tree, following the law of fall proposed by Galileo in print some 30 years earlier, the young student wondered what might cause the apple's acceleration. Why did it speed up as it fell, when both Galileo and Descartes had said its natural motion should be to move with a constant speed? Of course, both had said forces could cause objects to speed up or slow down. Descartes, in fact, had gone so far as to indicate that such forces were the results of the collisions of corpuscular atoms and the vortices they carried with them. But where were those things in the fall of an apple through space? What was the force that seemed to reach across the distance from the earth to the apple to grab hold of it and pull it with ever-increasing speed towards the earth's surface? As the student pondered this question, holding it in his mind before the power of his incandescent intellect, his gaze fell upon the crescent moon, and in that moment he had a realization. The moon traveled along a path through space that was a nearly circular orbit. Like the apple in its fall, this too violated Descartes' law of inertia that stated that the natural motion of an object was to move in a straight line at a constant speed. Here again was evidence of a force acting across space, pulling another object towards the Earth. What if the two forces were one and the same? What if the force that accelerated the apple also accelerated the moon? What could that force be, and how could it be explained? These questions, it was said, would trigger off an explosion of thought and work that would, some 22 years later, fundamentally transform how humanity understood the physical universe and forever alter the trajectory of human progress in setting the stage for both the Enlightenment and the Industrial Revolution. The young, 24-year-old man was, of course, Isaac Newton. Did he really sit in an apple orchard on a fall evening in 1665 and watch the fruit fall from the tree in a story with profound biblical resonance? This was the story he told his student in his old age, and it was the one that was passed on to the young Frenchman Voltaire, who was amazed that a man of simple country origin could rise to a position of such reverence that he would be afforded a state funeral upon his death, where his casket was carried by the cream of British nobility. This week we look at the work of that most enigmatic of men, who unraveled the mysteries Kepler and Galileo had first tried to understand. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 27, A New Physics. As we begin a series of episodes on the life and work of Isaac Newton, we will follow a pattern that I hope is familiar to you. In this episode, we'll look at almost strictly just his mathematical and scientific contributions so as to understand his place in the broader narrative that we've been exploring in this series. Then, in a series of biographical episodes, we'll look at the man himself along with the full breadth of his intellectual contributions and personal interactions in what can be seen as a tremendously pivotal period in both English political and social development, and the development of a culture of science that lasts even to this day. As such, I would like to leave aside for the moment Newton's caustic personality, his bitter feuds, his work in optics and alchemy, and his religious views to focus on his contributions in physics and mathematics insofar as they relate to understanding the Earth's place in the cosmos. Okay, with that said, let's get started by doing just a bit of biographical introduction. You see what I did there? Wasn't going to do biography, but you got to do a little, right? By most accounts I've found, Newton was born on Christmas Day of the old Julian calendar in 1642. As Great Britain was a Protestant country, it had not adopted the calendar reforms of Pope Gregory VIII as put forward in 1582, and thus the dates we have for these sorts of things can be a little bit out of sync. On the Gregorian calendar, the one that we use now, Newton's date of birth, assuming that the Christmas Day assignment is correct, would have been January 4th in 1643. He was born in Lincolnshire to a somewhat well-off family that had some land and a bit of status but no title. We know that his father, also named Isaac, was illiterate as he signed documents with an X, and that he died 3 months before his son was born. Newton's mother would marry a local pastor a few years later, and as the man had little interest in raising another man's son, young Isaac would be shipped off to a grandparent's care for a time. We know that as a youth, Newton was inquisitive and liked to build things with his hands. He made a number of small working models of things like mills and other machines, but his greatest fascination seems to have been with making clocks. This interest and fascination with time would be something he would return to in his life and work. Newton was something of a mediocre student for the most part, but not due to a lack of ability. While no one seems to say it, what comes across is the sense that Newton just didn't find schoolwork all that engaging in comparison to the other things that vied for his attention. What seemed to motivate him to take the work seriously was a serious competitive streak that he seemed to have. When the headmaster of his school felt that Newton was letting his study slip, he would promote another boy ahead of Newton. This slight would be all that would be required to coax the required effort from him to excel at whatever was being studied. On the completion of the traditional English schooling usually given to young men of some means at this time, Newton was recalled to his home where his mother hoped he could be pressed into service in running the family farm. He was terrible at it. The whole thing held no interest to him, and soon it became clear that he was singularly unsuited for the task of attending to the numerous mundane little bits and pieces of running a farm that were needed to do things like, keep the animals on their land and the like. Fortunately, a family friend who was a graduate of Trinity College at the University of Cambridge intervened and suggested that Newton be enrolled there to earn a degree and pursue one of the career opportunities that a university education might open for him. While his mother did acquiesce to the plan, she declined to put up the money to send him. As a result of this, he had to enroll as something of a valet to students who paid the full cost of their attendance until he was able to win enough scholarships to set himself up in a more independent way. It was during his time of study at Cambridge that the last truly great wave of the bubonic plague swept through England in 1665. This outbreak killed something like a quarter of London's population, and those who had the means to leave the city early in the crisis did so, which left it just an empty shell through the hot summer and early fall months. As a result, Cambridge suspended classes for the term, and Newton went to spend the time on the farm of the family. It is at this time that Newton is said to have had the epiphany regarding the attractive force that pulled both the apple to the surface of the earth and the moon around in its nearly circular orbit. Now, before we jump into that matter a bit more fully, let me make a few more comments regarding that larger picture, both in England and in the culture of scientific investigation. Much of Newton's early life was shaped by two events. The first of these was the English Revolution or Civil War, where the forces of Parliament and the forces of the king fought over whom would be the prime political power in the country. While Newton was too young and too distant from the centers of power to have a sense of the issues or to be really involved in everything that went on, he would have experienced the uncertainty and chaos of armies moving through the countryside, taking what they needed to survive from the people who occupied the land. This period would come to an end with the beheading of Charles I and the establishment of Cromwell's Commonwealth, built on the principles of a reformed version of Protestantism based on the theology of Calvin and his followers. This period would reinforce Newton's sense of the centrality of God and religion in his life, and while Newton's theology would soon diverge from that held by most of those close to him, his faith would, in many ways, be the driving motivation for all of his work across a broad range of disciplines. As a side note here, for those who are interested in knowing a bit more about the specifics of this period in English political life, I would heartily recommend Mike Duncan's Revolutions podcast. The first 15 or so episodes specifically look at the political history of the English Revolution or Civil Wars or whatever one might want to call it through the Commonwealth to the Restoration, as is done with his usual wit and attention to detail. Mike's been on hiatus for the last part of 2016, and he's just released his first new episodes of the Revolutions podcast in about a month or so, and I have to say, it's just great to have him back. The other thing we need to mention here is that with the restoration of the monarchy and the ascension of Charles II to the British throne, there was something of a release of pent-up energy. While Charles I had been a taciturn and stubborn man, and Cromwell was, well, Cromwell, with all of the religious restrictions and the, this could lead to dancing stuff, Charles II was something very different. He was a very libertine ruler, something the English people probably really needed at that point. As a result of this, there were a number of new enterprises established, including the Royal Society for the Advancement of Knowledge in 1662. An outgrowth of an idea first put forward by Francis Bacon, the Royal Society was an organization given over to the idea that a physical demonstration was of greater value than an eyewitness account, no matter how credible the eyewitness might have been. The central figure in the society in its early years, and key to establishing it as a truly worthwhile institution, was the Reverend Robert Boyle, whose work in both alchemy and atmospheric pressure formed much of the early meeting agendas. With Boyle were his two young protégés, the small and somewhat misshapen Robert Hooke, and the tall, handsome, and charming Christopher Wren. Boyle had hired Hooke as a technician and an instrument maker when the younger man's acumen for such things became apparent early in their acquaintance. Hooke had built Boyle's first good vacuum pumps and was always on hand at society meetings where it was used to make sure that it functioned properly. As we mentioned in an earlier episode, it would be Hooke who would independently discover many of the principles of both pendulum clocks and the nature of circular motion. When London, still recovering from the plague of 1665, was significantly damaged by the Great Fire of 1666, it would be Hooke and Wren, along with some others, who would be responsible for the urban plan for and the rebuilding of London's central districts on a more orderly and rational ideal. Hooke would have a great part to play in the life and work of Isaac Newton. Okay, let's talk about that fall on the farm just a bit more before we get into the meat of the material. Newton's first real interest in mathematics and physics was likely spurred by attending the lectures given by Cambridge's first Lucasian chair of mathematics, John Barrow, in the winter of 1664-1665. It was during this time that Newton read Descartes' Geometrie, which laid out the analytical geometry for the first time, as well as Francois Vidé's work on algebra and John Wallis's work on what's known as the method of indivisibles, which is an early precursor to calculus. Using this and Euclid's elements, Newton mastered conic sections from nearly every different perspective, something that would prove really foundational to all of his later work. Near the end of 1664, he figured out how to measure the slope of a curve at any point, a problem known as the problem of tangents that is intimately related to what would become known in calculus as the derivative. Building on Descartes' method of looking at lines perpendicular to the curve at a given point, Newton examined how these quote-unquote normal lines would change if examined at 2 points on the curve that were arbitrarily close together. This method of what is called infinitesimals would lead directly to the process we know as differentiation in calculus. It was also during this time that he was considering how to calculate the area under a curve. This, of course, requires just a bit of explanation. When looking at a function on a graph, that function can be represented by a line or, if the line is not straight, something we call a curve. If you think of this line or curve being drawn on an xy coordinate system, you can imagine that there's an area between the curve and the x-axis. If the line is straight and horizontal, this area can be calculated by determining the area of the rectangle that's created by the line and the zero axis or the x-axis. If the line is straight but has a slope, you can do a similar calculation, but you have to do it using a combination of a triangle and a rectangle. If the line is a curving function, then what you have to think about is breaking that line into a series of thin slivers, and then finding the area of each sliver using a combination of a rectangle and a triangle. Once you've done that, you can add all the little areas together to get the total area under the curve. Now, any way that you do this for a finite number of these little slivers will be an approximation of the real area, as all the angled sides of the triangles will not quite match the curve over the interval of that sliver that you're taking. However, the more slivers you choose to calculate, the better the approximation will become. The more slivers, the thinner each sliver will be. What Newton did, and this is just truly the brilliant thing, is he developed a way to figure out what will happen if you were to imagine slicing the area under the curve into an infinitely large number of slivers that were infinitely thin, and then adding all the infinitely small areas together to actually get, and this is the amazing thing, a finite number. The method he used was an extension of Wallace's indivisibles known as quadratures. He was able to show that the tangents of the curve and the quadratures approach were actually inverse mathematical functions of each other. And it was from this that he was able to make two very important advancements. The first is known as the Generalized Binomial Theorem, a mathematical tool for determining the value of certain types of equations. And, more importantly for our story, the other thing that he did is he began to imagine curves on graphs as being produced by a single point that moved along the graph to sort of carve out the shape of the curve. He referred to the rates of this motion as quote-unquote velocities at a given time. This new picture led him to conceive what he called the Fluxional Calculus, so named because of the picture of the values of the curve flowing from one point to the next in a smooth and continuous way. This picture would not only allow him to imagine infinitely small changes, which could be either understood as changing tangents or added together in what could become the derivative and integral, familiar to tormented college students the world over, though I have to say that the modern notation for said mathematical operations is much closer to the calculus's other inventor, Leibniz. But it also committed Newton to a dynamic view of the mathematics, where the curves were created by movement through space. This dynamic or kinematic view of functions would be profoundly influential when Newton began to consider the motion of real objects in real space. Newton's work on fluxional calculus was put forward in a brilliant essay published in October of 1666, and it marked him as one of the world's foremost mathematicians. This date, however, gets us just a bit ahead of ourselves. Newton was awarded his Bachelor of Arts in August of 1665 and had the scholarships needed to allow him to continue forward at Cambridge so that he could earn his Master of Arts in the course of the next few years. It's clear that his mathematical work of the previous year was foremost on his mind when, in the fall quarter at Cambridge, everything was suspended on account of that plague in 1665. Newton would return to his family home and, interestingly, would stay there for nearly 2 years working on a variety of projects, even as the university reopened its doors just 6 months later. It would be during this absence that the essay on calculus would be published. It would also be during this time that the apple would fall from the tree, if, indeed, an apple did fall from the tree. While we don't know to what extent the events of the apple and the legends are true, it is clear that while on leave from the university, Newton began to consider motion in great detail, especially where it connected to keeping a revolving body on its closed trajectory around some point. For the moon, this obviously meant its orbit around the Earth, but there were a whole class of problems that showed similar forms, such as the spherical pendulum we discussed a couple of episodes ago. What we do know is that Newton carried with him a sort of notebook where he jotted down his ideas on a variety of topics, including motion. In this quote-unquote waste book, as he called it, Newton recorded over 100 axioms of motion, things he held to be true for a variety of reasons. These statements should be understood to be specific in nature rather than the much more general laws of motion that would later appear in the Principia, but they would form the basis for that part of the great work. Among the most notable are those that show Newton clearly embracing the idea of inertia, as well as an embryonic form of the law of action and reaction, now known as his third law of motion. He also seems to have worked out a fairly complete form of an idea we need to spend just a few moments discussing related to both of these, that of momentum. As we've mentioned in previous discussions of medieval physics, it had been known for several centuries that Aristotle's picture of physics had been flawed, and so there had been attempts to reform it in ways that kept most of the features of Aristotelian motion while bringing it into line with more carefully made observations. The idea that had emerged in several forms was that of something called impetus. The idea was that when a force was applied to an object, it gave that object impetus, a quantity of motion associated with the body. It was thought that as the body moved, it used up its impetus until it ran out of it, at which point the body stopped. A good way to think of this is that impetus is a bit like gas in a gas tank in a car. When you gave the box a push across the floor, the applied force gives impetus or puts impetus in the object's tank. As the object moves, in this case, think of a box sliding along the floor after you've stopped pushing it, that object uses up the gas in the tank until it runs out and it comes to a stop. In some versions of the hypothesis, the velocity of the object was related to the amount of impetus, so that the less impetus something had, the slower it moved. Now, if you kept pushing in this model, you kept adding impetus even while it was being used up, and so the object would keep moving and moving at a constant velocity. Now, to be honest, for forced or violent motion, as it was called, this is actually not a bad little hypothesis. It's pretty good in a lot of ways. The problem you run into with it, though, is how does it explain natural motion, i.e. the fall of heavy objects or the rise of light ones? This is where Galileo's work on the motion of objects was so important. It showed that the impetus model couldn't work to describe the motion of accelerating objects, i.e. objects that sped up or slowed down. While Galileo did introduce the idea of inertia, he didn't really go beyond that, though. Descartes, of course, had extended that idea and had introduced a collision-based way of explaining how forces produced motion, but this too proved problematic. What Newton did was go back and look more carefully at the impetus idea and modify it quite a little bit. What he said was that objects did possess a quantity of motion, but it was something different, something he called momentum. Momentum, he said, was the product of an object's speed and something associated with the bulk of the object. He said that this quantity was not used up by the body's motion, but rather it was something that can only be moved around between objects through collisions. While momentum would be the central idea around which all Newton's subsequent thoughts on motion would take place, at this point he only developed in detail a description of how the total momentum of two bodies involved in a collision would be conserved, with only a certain amount of the quantity being transferred from one object to the other during any sort of interaction. This law of conservation of momentum was a groundbreaking piece of work that stands as foundational to physics even today. From this, Newton considered the problem of a body bouncing around inside a square box, as it were. In this particular thought experiment, he considered a spherical object that traveled somewhat parallel to a wall of the box, but still moving towards it in what we might think of as an oblique path. This object, or sphere maybe, would encounter the wall and would have part of its motion, the part perpendicular to the wall, reversed, while the part parallel would remain unchanged due to the conservation of momentum. The ball would then continue on to the next wall of the square where the process would repeat itself. In each case, as the ball hit the wall would exert a force on the box in order to reverse its perpendicular momentum. This would mean that the ball would travel in all four sides, or around all four sides of the box, in sort of a four-sided orbit. And that orbit would be around the center of the box, with the impulsive force of the sides of the square on the sphere towards the center as well, providing the thing that redirected the sphere and kept it in the orbit. What Newton then did is he increased the number of sides of his container until there were sort of an infinite number. And that, of course, when you take a square and then you make it a pentagon and a hexagon, etc., as you take that infinite number of sides, the square becomes a circle. And this process towards an infinite number of sides, of course, was something he was now really well equipped to handle based on his work through 1664 and 1665. And as he did it, he was able to show that the orbit of the sphere would be a circle, and that the side of the now spherical circular container would exert a constant force towards the center of that circle that was proportional to the square of the sphere's velocity and inversely proportional to the circuit's radius. This, of course, would be the same result that both Hooke and Huygens would publish later, though each of them would discover it through different means. Once this was done, Newton was now ready to consider the orbit of something like the moon around the Earth. In his first attempt, he seems to have worked from Galileo's assumption that an object's natural motion was more or less circular, and that there was a centrifugal force, or a force away from the center of motion. Hence, he tried to balance that force with an attractive force that would pull the objects back into a circle or towards the center of the Earth. He first calculated the acceleration of a falling object near the Earth's surface and then compared that to the centrifugal force and concluded that his attractive force, something he was beginning to call gravitas or gravity, had to be about 350 times bigger than the centrifugal force at the Earth's surface. He then repeated this type of calculation for the Moon. By comparing these two calculations, he was able to derive that the force that attracted the objects to the Earth's surface was the same as the force that pulled the Moon into its orbit around the Earth. The force had to get weaker the further one was away from the Earth's center, and the function that described that weakening depended on the inverse of the distance squared from the center of the Earth. This work, while limited and still inaccurate in many respects, specifically as related to centrifugal force, shows that Newton had worked out the basis for what would eventually become his universal law of gravitation. During this 2-year hiatus from Cambridge, Newton worked on a number of other problems as well, most notably things in optics, philosophy, and theology. In 1667, he returned to the university and was soon made a Fellow of Trinity College, something that would eventually require a bit of sleight of hand to make happen due to Newton's emerging religious beliefs, something we'll discuss in greater detail in our biographical episodes. In 1669, he was elevated to the Lucasian Chair, where he lectured on mathematics and his work in color, light, and optics. Not long after this, he built his first refracting telescope to overcome the problem of chromatic aberration posed by refracting telescopes. This earned him election to the Royal Society, where he was encouraged to present his optical work. This work and its presentation would embroil him in a dispute with Robert Hooke that would traumatize the sensitive and reclusive Newton. As a result, he would withdraw into a state of semi-seclusion at Cambridge for the next decade, working more or less in obscurity, while the scientific community in London continued to struggle to understand the orbits of the planets in the solar system. A solar system, by the way, that was more and more coming to be seen through the heliocentric and Keplerian sensibilities. It was during this time that Newton would take up the study of alchemy in secret, as such practices were banned in England and in many other places in Europe, and if he were discovered and then convicted, he could face the sentence of death. For nearly a decade, Newton corresponded with only a few other scholars and just once with the Royal Society over the issue of refraction in optical systems. However, in 1679, his mother passed, and as often the case, when one's parent dies, the event seems to have spurred something in Newton to re-engage just a little bit. On the day in November that he returned to Cambridge, a letter from Robert Hooke arrived for him. Hooke was writing to ask if Newton had anything he might want to submit for consideration by the Royal Society. Over the last few years, the organization's novelty had worn off and very few scientific matters were being submitted for consideration. That some of this fall-off may have had to do with Hooke's own tendency to claim that any discovery that had been made was merely a copy of some piece of work he had already done was apparently lost on him. Nevertheless, as part of the letter, Hooke rather collegially asked what Newton thought of an idea he had about a thought experiment, wherein a ball would be released from a very, very tall tower and that would be allowed to pass through a hypothetically transparent Earth. Hooke suggested that the body would fall straight to the center of the Earth while constantly accelerating. Newton, rather surprisingly, replied that Hooke was mistaken. The body at the top of the tower would have a greater velocity and thus would track ahead of the base of the tower. As it passed through the transparent Earth, however, it would travel in front of the center and then spiral around it until finally coming to rest there. To this, Hooke responded that while he accepted Newton's analysis of the motion of the falling body in the initial part of the fall, he disagreed with the portion where the object would spiral around the center of the Earth. He suggested instead that the object would travel in an elliptical path around the Earth's center back to the top of the tower and thus enter into a Keplerian orbit. Now, if this all seems a bit confusing, we'll post a diagram of Newton's ideas, and if we can find a good picture of them, Hooke's ideas as well, at the podcast website, thescientificodyssey.typepad.com. The two men then exchanged a couple more letters discussing the problem and associated issues, including how to reconcile the possibility of an inverse square law for the force of attraction with Kepler's elliptical orbits. This final comment got Newton to thinking about how his ideas regarding motion, first conceived some 15 years earlier, might be applied to both terrestrial and celestial motion. Shortly after this, Newton, using the ideas of momentum and calculus, demonstrated mathematically that elliptical orbits were consistent with an inverse square law for the force of attraction by using Kepler's second law of planetary motion, or what we sometimes call the law of areas. This is a really big step in this whole thing. Newton might have thought of an inverse square law was the way to go, but in showing that it produced the general mathematical forms that described Kepler's orbits and planetary speeds, he showed in essence that there was no other way that that force law could be. A year after this, in 1680, a great comet appeared in the sky over London and the rest of Europe, and became a source of great speculation. One of the individuals most involved in the observation and discussion of the comet was England's astronomer royal, John Flamsteed. Newton and Flamsteed corresponded about the comet. Shortly after the comet disappeared from the night sky, getting too close to the sun to be observed, another reappeared. While many, including Newton, assumed that the two comet events were separate, Flamsteed argued that in fact they were the same comet that had traveled towards the sun through attraction and then had been repelled by it as the comet got on the sun's opposite side. Newton initially rejected this hypothesis, as it made no sense to have the sun switch from attraction to repulsion for no reason. However, as he considered the idea, he realized that if he used his idea of inertia and the work he had done regarding the inverse square law of gravity, he could make the case that the comet had passed on the opposite side of the sun as it traveled on a parabolic orbit. And thus, the two appearances were the first time the comet came in on the incoming side of the sun, and then the second time we saw it from the Earth as it was going out away from the sun. This, of course, would mean that the sun exerted the same type of attractive force he had originally posited for the Earth with respect to falling bodies in the orbit of the Moon. In other words, gravity was no longer a merely terrestrial phenomenon, but instead a universal force. A conclusion that shattered the terrestrial-celestial distinction that had existed since the time of Aristotle, the distinction that both Galileo and Kepler had both unsuccessfully tried to overcome. The obvious conclusion from this was, therefore, for Newton anyway, to extend the various ideas regarding motion to all objects in the cosmos. This would spur him to re-examine the various ideas from his waste book of 1665 to 1667 and think more carefully about the full synthesis of the ideas he had written there. Of course, all of this was happening in Newton's state of semi-seclusion, so no one really knew about the work. No one knew what Newton was doing there in Cambridge. However, in 1684, the young Edmund Halley visited Newton at Cambridge to help settle a discussion that was often had in the coffee shops of London, most notably between Hooke, Wren, and himself. The discussion was whether one could determine what orbital path would result from an inverse square law. When Halley asked the question, Newton responded that he had already solved the relevant mathematics and demonstrated that it was an ellipse, or actually any of the conic sections, that worked with an inverse square law. As Newton searched his chambers for the paper, Halley quickly realized that the quest was likely hopeless, as Newton, like many academics, hadn't exactly kept an orderly system of keeping his work organized. Newton asked Halley to return at a later date, and he would have the appropriate derivations for him. While Halley eventually ended up having to wait about 3 months, in November of that year, Newton sent him a short and mathematically dense tract titled De Motu Corporum in Jarum, or On the Motion of Bodies in Orbit, which laid out the mathematical proof for someone who could work through it. Included as a part of this was an early version of what would become Newton's very famous second law of motion. I won't go into all of the details of the work, but it was clear to Halley that Newton had gone way beyond answering a simple question, and this was a work of just absolutely monumental importance. While there would be a number of twists and turns in getting all of this to publication, Halley would spend the next 3 years working with Newton to produce a comprehensive treatment on both terrestrial and celestial motion. This work, known as the Philosophae, Naturalis, Principia, Mathematica, or oftentimes it's now just called the Principia or the Principia, it put forward a number of fundamental ideas that completely revolutionized our understanding of motion. In the rest of this episode, I'd like to take a look at the ideas found in the Principia in a more direct way and make a few additional notes. The first thing here is to understand that the Principia was almost impossible to understand in many ways, and Newton wrote it that way on purpose. His various disputes with Hooke, Huygens, and Leibniz led him to create a document that was as mathematically impenetrable as possible. In this, his goal was to show that he and he alone had all the requisite tools and ideas to put everything together. The second thing to understand is that the physics of the Principia represents a complete and utter rejection of Aristotelian physics and astronomy in all of its tenets. However, as such, it is the first time since Aristotle where the motions of the cosmos are once again completely unified. No longer are there separate realms of natural philosophy and astronomy. The unification of cause and motion sought by Kepler was in the Principia realized. Not only that, however, also seen in the work was the principle of universality, the idea that the natural laws applied in all places in the cosmos. No longer were there separate rules for a corruptible earth and an incorruptible heaven. While this seems obvious to us now, this was such a profound paradigm shift that had not Newton's unification been so successful in predicting natural phenomenon, it would likely have been rejected out of hand. The third thing to note is that the first edition of the book, published in 1687, was not really the thing that shook things up. It wasn't the thing that really got everybody excited. While all of the ideas were there, they just weren't usually expressed clearly enough for anyone else to really get their handle on. It wouldn't be until the second edition, published in 1713, that Newton's ideas would really catch fire and spread throughout Europe. As we'll discuss in the biographical episodes, this was due to the work of one of Newton's few close friends, who really helped him rewrite parts of the book to make them more understandable and accessible. So what's in the work? Well, one thing is a restatement of his version of the calculus. Interestingly, while he put forth his version in some detail, he doesn't actually use it much in the portions on physics. The reason for this is that most of his readers would have been unfamiliar with the ideas found in calculus, and thus any proofs of the physics that relied on it would be more or less incomprehensible to them. Instead, Newton used a great deal of geometry, specifically the geometry of conic sections, to demonstrate many of his conclusions. While this was more accessible then, it is nearly incomprehensible now due to the replacing of those kinds of tools with the more advanced methods of calculus. As an interesting story, when Richard Feynman gave a lecture on planetary motion from the Principia to the students at Caltech, it took him months to work through the various proofs that Newton had used. When Feynman's lecture was rediscovered years later and published, the editor of the document had to take a month-long cruise and lock himself in his cabin to be able to focus sufficiently on the work to figure it out. In other words, the stuff that Newton was doing here wasn't really very simple at all. The next thing we should talk about is Newton's explanation of a property that he said all matter possessed, something he called both mass and inertia. Nowadays, when we use the word mass, most of us think of it from a chemistry-based definition, that being all matter that makes up an object, the total number of atoms or something like that. But Newton is working at a time when there were real questions about what the nature of matter was. As such, Newton developed a very different definition for mass. It was that property of an object that resisted a change in the object's motion. If you think about pushing an object across something that doesn't have a lot of friction, say something like ice, when the object is pushed, it will speed up by a certain amount every second. Now, if you were to repeat that experiment with an object with twice as much mass, there would be twice as much resistance to that change in motion, and the object would only speed up at half the rate. And so at this point, this all kind of feeds into Newton's three laws of motion, and so we should spend just a little bit of time talking about those here. And I don't want to get into all of the details here because that's something that would happen in a physics class. If you're interested in sort of finding out more about that, I do have a YouTube channel. You can search DRC Davies out on YouTube and find my YouTube channel where I spend a lot of time doing some videos on the various types of things in physics, and I've got a number of videos that specifically talk about Newton's laws there. The first law is really a restatement and an expansion of Descartes' law of inertia. What Newton says that an object in a state of motion will remain in that state of motion unless acted upon by a net external force. Now, the thing that's interesting here is there's a little bit of code involved in part of this. What Newton means when he says a state of motion is he's really talking about an object traveling with a constant speed in a straight line, what we call constant velocity. And so what Newton's saying here is inertia says that an object's going to travel in a straight line at constant velocity and not change from that unless there is a net force that acts on that object. And this leads to his second law. The second law describes what will happen if a net force is applied to an object. Now, the way this law is usually expressed is something like the sum of the forces equals the mass times the acceleration. But I think the better way that Newton looks at this is, first off, he looks at it through the lens of momentum, which is probably further than we want to go here. But the other thing he does is he sort of thinks about it in terms of this change in the velocity, the change in the rate of motion. And so in looking at that, what he says is that if I take all of the forces acting on an object and I add them all together, so if we think of, say, a box that's being pushed across the floor, if I take a look at all of the forces acting on that box, I have a push maybe to the right, and I have, the floor pushing up on the box, and I have gravity pulling down on the box, and then I know that I've got friction that opposes the motion. Now, if all four of these forces add up to zero, then we have zero net force, and we're back in the first law. The object's going to move at constant velocity. But if my push force is greater than that friction force, what Newton says is it's not that the object will travel at a faster constant velocity, but rather instead that the object will begin to speed up, and as long as I can push harder than the friction force sort of tries to slow the object down, that object will continue to speed up more and more and more. Conversely, what Newton also says, and we've talked about this already, is that the more mass the object has, the less acceleration it will experience. But note, as long as there's a net force, no matter how much mass you have, there will be an acceleration. It's just if you have a lot of mass, the acceleration will be very small. An example I talk about with reference to this is in my physics classes. I talk about this old carnival trick that used to happen back in the 1800s and the early 1900s, and that was sort of one of these world's strongest men can pull a locomotive down a track just using their teeth. And the idea is what you would have is the carnival would come into town and the locomotive would be placed on the track, and the world's strongest man, on the day before the carnival as a way to sort of gin up some interest in what was going to happen. The world's strongest man would be, hooked to sort of a harness kind of thing where he would bite down on this piece, and then he would sort of pull, he would lean back with his legs and his shoulders and he would pull, and eventually he could get that train to move, and then everyone would just be really, really amazed by all of that. And that is a pretty amazing feat, don't get me wrong. And that guy's got to have some pretty strong choppers there to keep everything together. But what's going on there is actually just a pretty specific and simple application of Newton's second law. What would happen in that case is the locomotive has an enormous amount of mass, just a huge, many tons amount of mass, right? But what they would do is they would make sure that they had disconnected the engine from the actual drive train or the wheels of the train so that you didn't have to overcome the friction in the engine. And then what they do is they'd make sure that all the wheels were really well lubricated. Now it turns out that the wheels rolling on steel, that's actually a pretty low friction process in some respects. And so the thing that's really great about that is the world's strongest man, according to Newton's second law, doesn't have to overcome the mass of the object. All the world's strongest man has to do is overcome the total friction force in the drivetrain of the train. And once he does that, the thing that's really interesting is, as long as his friction or his pulling force is just a little bit bigger, if he pulls for long enough, he will actually get the train not only to move, but to accelerate. And that was something that, of course, these folks in the carnivals would use to sort of, get everybody excited about. We have these really amazing acts. The third law of motion, however, is a little bit different than the first two, in that instead of talking about the motion of a single object, it talks about the interaction between two objects. What it says is, when an object experiences a force from the environment, usually from another object, that object will exert a force back into the environment that is equal in size and opposite in direction as the force it experiences, and the force it exerts will be of exactly the same type. And this turns out to be really important, because what Newton's able to show is that when you look at the Earth and Moon system, what you've got is you've got the Earth and you've got the Moon. And if the Earth exerts a gravitational force on the Moon, then the Moon has to exert an equal and opposite gravitational force back on the Earth. Now, the thing that's really interesting in this, you might ask, then, is, okay, wait a minute, why don't the two objects orbit each other? And this is where that second law thing becomes so important. Even though the force between the two objects is exactly the same, because the Earth has so much more mass than the Moon, it accelerates significantly less, but doesn't accelerate a zero amount. And so Newton is able to use this to explain that wobble of the Earth, that precession that we talked about often in our very early episodes. These three laws come together to sort of describe not only the motion of objects in the heavens, they also describe the motion of objects on the Earth, as we sort of implied in some of the examples that we use. Now, the final thing we want to discuss in this consideration of the Principia is the final version of the universal law of gravitation. Here, Newton says that mass has one other thing that it does. It produces force or exerts force on other masses. He says that this force is directly proportional to the product of each mass and inversely proportional to the square of the distance between the two masses. And he says that all mass does this. Now, the implication of this is really interesting. If you're listening to this podcast while driving down the road with your friend, I have to tell you that both you and your friend are attracted to each other on a very deep and physical basis. And that's because you have mass. There may be other reasons, I don't know. But the thing I'm talking about here is you have mass. You have mass, they have mass, and masses attract each other. So the question then comes up is, why aren't you just immediately pulled together? Why don't the forces between the two of you pull each other together and stick you to each other? Well, it turns out that the gravitational force is an extremely weak force. While Newton wasn't exactly sure about how weak it was, he knew that something had to have a lot of mass to attract other mass. In fact, he knew that it had to be sort of planetary amounts of mass. And so, from these three laws of motion and the universal law of gravitation, Newton is able to derive all of Kepler's laws of planetary motion, as well as the results of terrestrial motion experiments that have been conducted before his life. Thus, in 1715, even though there was still no direct evidence of the Earth's motion, only those who were either ignorant of Newton's work or ideologically hidebound denied the heliocentric model of the solar system, and specifically Kepler's version, his elliptical orbit version of that motion. It's not that there was more evidence that had been discovered, but rather the evidence that already existed had now been explained in a comprehensive model that accounted for all of the observed phenomena in a way that was vastly superior to anything else. And I think that's really, really an important point. And so let me state it again. It's not that there was any new evidence. There was no new data. There were no new facts. What there was is there was a new way to understand those facts in a greater fashion that solved more problems and dealt with more issues and made better predictions going forward. And so because of that, the Newtonian model, the Newtonian synthesis, as it were, made all of that come together. And it is here that I'd sort of like to make one final point. If you go all the way back to our first series of the 5-episode podcast thing that we had about sort of the scientific method, you'll find an episode I titled, What's the Big Idea? In it, I talk about the difference between hypotheses and laws and theories. You'll note that nothing that Newton has here is actually called a theory. There's no theory of gravitation here. It's a universal law of gravitation. Everything is thought of as a law of nature, and there are two reasons for this. The first is that the ideas of hypothetical and theoretical thinking are just beginning to be developed at this time. That, it starts kind of with Boyle and then moves forward. Had Galileo had such tools at his disposal, it's been suggested by a number of authors that it's somewhat likely that he might have been able to avoid many of the logical contradictions and traps that bogged down his defense of Copernicanism in 1616. The second thing here to understand, though, is that nothing in Newton's work really attempts to explain the whys behind his ideas. While he explains sort of why planets move in ellipses or why objects fall with constant velocity, he doesn't explain why those rules are the rules that nature follows. He does offer some suggestions from his work on alchemy and astronomy, but he's very much uncomfortable in raising them above the level of speculation, even though he was deeply committed to them. Instead, as the famous statement goes, he offered no hypotheses to explain the universal law of gravitation, rather than saying it was just a mathematical demonstration that would account for the observation made of the motions of the heavenly bodies. Newton didn't know why the second law of motion worked. He just knew that it accurately predicted what an object would do in every case where the forces on the object were known. All in all, the Principia is a powerful piece of work, and it established Newton as the premier thinker in all of Europe. Ironically, the publication of the second edition of the Principia would more or less mark the end of his scientific work. Following this, he would give his time over to the running of England's mint and writing theology. Those, however, are topics for another episode. As we bring this week's explorations to a close, let me once again thank you for being part of the crew. I really appreciate the time and the interest that you give this podcast and what we do here. Be sure to check out our website or like our Facebook page if you'd like to sort of keep track of what's going on and look at some of the additional material we post there to help you understand what's happening in some of the narrative that we're producing. If you have a few minutes, would you mind leaving us a strong review on whatever service you happen to use to enjoy the show? It really helps us get the word out. Also, if you think you know someone who might enjoy the voyage but isn't a part of the crew, consider sharing the podcast with them. Over the course of the next couple of weeks, we're going to take a look at the very complicated life of Newton. It's going to be a bit of a wild ride, as he is a very complicated and somewhat exhausting person to deal with. As I've been doing my research for this episode, I've come to think of him as this really fascinating but sort of obnoxious house guest that you've invited to stay with you. Maybe, for those of you who watch the show Big Bang Theory, maybe like, Sheldon Cooper, but with less social skills. He's kind of like one of these people where sometimes the dinner conversation is really fascinating, and sometimes he says and does stuff that just makes you want to punch him in the nose. Also, in reference to my research sources, I'd be remiss if I didn't mention those, so let me sort of list off a few of the things that I've been using besides just my own training in physics. Right now, I'm working with James Gleick's biography of Newton, and also Rob Iliff's short biography in the Oxford Very Short Introduction series. Added to that, I'm using Alan Chapman's Stargazers, and Edward Dulwick's Clockwork Universe, and finally taking a little bit from Wooten's The Invention of Science, which just seems to be showing up over and over again. And I'm sure I'll add to this a bit by bit as time goes on. A couple of sort of just quick review notes on these. Dulwick's book is really good if you want to get a sense of both the time period in England and also the development of some of the mathematical ideas. And Iliff's biography does a really nice job of showing the integrated nature of Newton's worldview across all of the disparate areas of research and writing. Gleick's biography is really solid. I'm not sure it quite rises to the level of his biography on Feynman, but it's really quite good and sort of gives you a sense of just Newton as a human being and sort of tries to approach that sense of what was his genius. Now, like I said, that's a whole lot of Newton, and I'm sure that when we're done with him in a few weeks, we'll have both a real appreciation of that genius that Gleick mentions, and we'll also sort of have a desire to buy him a bus ticket out of town. So anyway, again, thanks for listening and being part of the crew, and until next time, full sails on your journey.